afternoon or good evening, depending on where you are. Welcome to the 2025 summer virtual course for satellites and fires, organized by the American Meteorological Society Satellite Meteorology, Oceanography, and Climatology Committee, called the Satmoc Committee. So the Satmoc Committee has been organized a virtual training course for free in the past 4 years or so. And in this year, we organized our short course centered around the fires. So the course has 4 sessions. We start with a session about the introduction of satellite remote sensing, and then followed by 3 sessions focused respectively on the pre-fire, active fire, and the post-fire phase. And today is the fourth and the last session, but not least session about a post-fire that what satellite can study about them. And the session will last from 9 a.m. Eastern Time to 1 p.m. Eastern Time, about 4 hours. And before we begin, I'd like to give a little bit of introduction here. So the Satmoc Committee has a working group for the virtual training that consists of those members whose name you can see from your screen. My name is Jun Wang from University of Iowa, and in the past half year, the working group has been working together to come up with the session materials, to come up with all the logistics, and in particularly, I'd like to thank Gary McWilliams, who has been on the bookkeeping and organize all the sessions, organize all the training meetings in the last half year. I also like to thank Megan Christensen, who hosted the meeting, set up the Zooms and did this, and many other logistics. So today our session will be led by Javier Villegas Bravo, who is a faculty specialist at the University of Maryland, also in the Cooperative Institute for Satellite Earth System Studies with NOAA. And Javier has a bachelor degree in atmospheric science from University of Illinois at Urbana-Champaign, and a master degree in atmospheric science also from the UIUC. He is an expert on the satellite imaging studies, including wildfire burn area detection and its effect on flash flooding. Very interesting topics. In addition, I also have 2 announcements to make. One is that there will be a NOAA satellites hackathon coming in October 2025. If you scan the QR code on the bottom right, you will be able to get the link and join this competition. But there are also subject matter experts and mentors that can help you along the way while you participate those competitions. So it's a very good resources, also good community that you can join in. So you are welcome to join in the hackathon competition in October. Finally, all the slides, including the training session that are recorded, will be shared with you through the link that you can find in the chat in a minute. And also, if you have any questions, please, in the session, you can direct them through the Zoom QA functions down in the toolbar of the Zoom. So with that, I give the floor to Javier. You take it over then. Thank you.
Thank you, Jun. Can y'all hear me okay?
Yes, we can hear you.
Yeah.
All right, perfect. All right, I'm going to share my screen. Okie dokie. The slideshow up. All right. Hi, everybody. My name is Javier Villegas Bravo, and today I'm going to be giving a short course on post-fire hazards. And I'll be focusing on burned area satellite analysis and applications to flash flood forecasting. So yeah, I got my BS and my MS from the University of Illinois at Urbana-Champaign. And for my master's thesis, I did cloud detection. I made a cloud detection algorithm using MODIS for an upcoming mission called Maya, which is an aerosol mission. So I have a lot of background in image detection and pixel classification from Earth observing satellites. Now I'm a research scientist at the University of Maryland, Cooperative Institute for Satellite Earth System Studies, or SISES. And that's a cooperative institute with NOAA. So the way we get our grant money, we usually sit with a team at NOAA. So I am the satellite liaison at the NOAA National Weather Service Operations Proving Ground. And there we test and develop, or it's my responsibility to test and develop satellite products for operational use in the United States National Weather Service. Some of my day-to-day responsibilities are developing satellite products based off operational needs. So I talk to the forecasters and I get familiar with the products that they issue. I know all about the satellites that we have at NOAA, NASA, and our international partners. And then I try and work with them to develop products. So I'm speaking with developers as well. So a lot of the universities here in the US and within NOAA and its cooperative institutes as well spend a lot of time doing this as well. And I talk to them and make sure that any algorithms and software that's relevant to satellite meteorology that can improve the forecast gets to the forecasters. Well, and evaluate those satellite products in what we call test beds. And in these test beds, we design experiments, we fly in forecasters, we do it virtually as well, and we simulate weather events or do live weather and simulate some scenarios to test the effectiveness of the products. And the overall goal is to bring the satellite products from research to operations to improve weather forecasting for the public. Okay, so for the session, we will focus on the post-fire flash flooding impacts of burned areas and mountainous terrain. Session should last about 3 hours with three 10-minute breaks as well. I created 5 questions that I hope you all be able to answer after this course. The first one is, why is tracking burned areas in near real time from satellite important? 2, what are the advantages and disadvantages to track burned areas using active versus passive satellite remote sensing and polar versus geostationary satellites for change detection, which is essentially what we're doing here. 3, how do burned areas recover and what's the impact change over time with respect to flash flooding? For where can you download and view this satellite data? So I'm going to show you like a NASA website. I'm going to have you register for an account and download the data. And this is how I download the data as a research scientist. So it's the real stuff. And 5, how do you open and manipulate the satellite data in Python to see burned areas? So at the end, I have, or the second to last thing I have is a coding exercise on Google Colab where we'll take the data that we downloaded, and I have an IPython notebook via GitHub, and I'll show you how all that works, but hopefully it'll be pretty easy. I think you may need a Gmail account. So why is tracking burned areas important? This is a diagram from the National Weather Service, and here on the left, before the fire, we have some trees, and I'm focusing specifically on mountainous terrain, so there's an inclination. This is important for the flooding aspect later on. Then there's a fire, and a lot of the vegetation disappears, and it leaves this layer of ash and burnt topsoil. The important thing is that this is hydrophobic, and there's very little anchoring the soil at this point. And the other thing is the incline of the terrain. So beforehand, if there was like a storm that came by and it had a normal rain rate, I don't know, like an inch per hour or something like that, or maybe less. Inch an hour is a lot. Maybe nothing will happen. There'll be no flash flood. But now with this burn scar in the way, it will allow the water to run down the side of the mountain much more violently. So this is an example from Jamestown, Colorado in September 2013. You can see the whole side of this hill has been burned, and all this gray soil is the ash that's left, and there was a debris flow from the top here all the way down. And the cartoon kind of illustrates the effects of this, and essentially the hazard from burned areas, given some rain and some inclined terrain, is this debris flow can destroy infrastructure and injure people downstream of it. So most deaths occurred where the debris flow residents who were like in the way of this debris flow or landslide. They get injured and they can even die. Here's some pictures just from like a news broadcast from the 2020, I think it was the Cameron Peak fires in Colorado. There was some rain afterwards, and there were some multiple debris flow events actually from this fire. And you can see how violent the debris flow is flash flooding. It's like completely destroyed this road here and causes a lot of destruction and moves a lot of mass. So that's why we want to track the burned areas. I talked to the forecasters at the Weather Prediction Center, which I'll talk about that center later. But they use burn scar maps to help issue their flash flood warnings. So first I'm going to talk about the physics involved in sensing these burned areas, and I'll go through some examples as well. So in this figure, on the y-axis on the left is reflectance. Reflectance is a value from like 0 to 100%, so how much light is getting reflected off the surface of the Earth from the sun. And then on the x-axis, we have the wavelength. I think it looks like it's in micrometers. And this green line is the reflectance you would expect at each wavelength for healthy vegetation. And this red line is the same, but for burned areas. So I want to bring focus to two bands. So 0.86 micrometers, which is on the left, circled in blue, and 2.25, 2.3-ish micrometers on the right. And you can see that the healthy vegetation and the burned areas have opposite signals. So in the 0.86 band, the vegetation is much, much brighter than the burnt area. And the 2.2-ish, 2.3-ish band, the burned areas have a lot more reflectance than healthy vegetation. So there it is in writing, and turns out we can make an index out of this called the normalized burn ratio. If you've ever heard of the normalized difference vegetation index, it's almost the same, except we don't use the red band, we use the 2.25 micron band. And the formula looks like this. That's the reflectance at 2.25 micrometers minus the reflectance at 0.86 micrometers divided by the sum of those two reflectance bands. And we can also create a false color RGB. It's called the Dayland Cloudfire RGB that we have like in the satellite community. So we take the red, green, and blue channels, but instead of putting the red, green, and blue bands from the satellite, we put 2.25 microns, 0.86 microns, and 0.67 microns, and I'll show you what that looks like. And before I move on, so the 2.25 micron band, or the red channel will show uh, all the burnt plant matter. 0.86 micrometers, that will show all the healthy plant matter. And the 0.67 micrometer adds like more like color fidelity, so you can distinguish between different uh, surface types other than like burnt and veggie. So this is what I call a primitive burned area mask that I developed, and we're looking at August 24th, 2024. And we're over the Western United States. I think California is like right here, and then here's like all the desert and the mountains, additional mountains if you go further east. So on the left is a normalized burn ratio. Um, so this feature here, for example, is a burned area from a wildfire, and these other red features here are burned areas. So the normalized burn ratio is high for burned areas. This area around here, this like yellow green area, that's like the desert. It has a similar signature to burned areas, but it's a lot weaker. And then the vegetation is this dark blue color. It's very low values of normalized burn ratio. This is the Dayland Cloudfire RGB, which shows the burned areas in red, healthy vegetation in green, and deserts in like this brown reddish color. And this is the mask that I developed on the right. And it just grabs just the burnt pixels, obviously with some minor errors. I'm just going to zoom in. So in the United States last year, late July into August, we had a very big fire in California called the Park Fire, which we're going to analyze later as well too, with some other maps. And you can see the normalized burn ratio is very high where it happened, and then the vegetation around it is very low. And this is actually the remnants of a fire that burned in 2021 called the Dixie Fire. So when the Dixie Fire first burned, it had a similar signature in the burn ratio to the Park Fire. However, over time, the vegetation has regrown and the signal has weakened quite a bit. And there's also a fire here, I think North Complex. This is a very active area for the United States. And over here is the mask. So on the right side, it's just normalized burn ratio again, but I've only picked out the pixels that have exceeded some okay complex thresholds. So I want to talk about some of the satellites that are available. We call these Earth observing satellite platforms, the ones that are like, relevant to meteorology. And the figure is a little small, but I want to go over just over like a couple of orbits that these satellites can take, and then a few instruments. And then we're actually going to go on some web viewers and view some imagery of the Palisade fires, another fire event that happened earlier this year in the United States. So this is the geostationary orbit, sometimes called the georing. And at NOAA in the US, we have two major satellites that goes west and goes east. And they cover the full disk of the Earth that's in their field of view. And they take an image of the Earth every 10 minutes. And depending on where you are, it could be like half a kilometer, 2 kilometer, or like, I don't know, even 10 kilometer resolution as you get closer to the poles. So you have the best resolution around the equator, and then it degrades as you get farther away. And over the US, we even have 5 minute and 1 minute imagery. So if a fire is going on, or if there's cloud cover and the clouds like are moving out of the way, geostationary satellites are really good for any kind of change detection problem. So that would include burned areas. And so they stay fixed relative to a longitude and latitude of the Earth. And polar orbiting, which is these red rings around the Earth, they circle around the Earth while the Earth spins within the orbit. So eventually the satellite will like go over the entire Earth, but it doesn't have the capability of these 1, 5, and 10 minute imagery. It's more like the revisit time may be daily, it may be every 2 weeks, depending on the coverage of the camera. One of the satellites, so there's a few polar orbiting satellites that I want to talk about. So Sentinel-2, which is owned by the Europeans, has a multispectral instrument, MSI, that takes like 10 to 20 meter resolution images, and it goes around, and it's used a lot for mapping these burned areas after the fact. Sentinel-1 is another European instrument. It's a radar that's mounted onto the satellite, and we'll talk about it more later, but it can see through clouds, and it can see through smoke. It can penetrate all the way to the ground, even a little bit into the ground, and it can detect surface deformations. And we'll talk about how you can look at burned areas using that. And then the last one is over here, SUMI MPP. SUMI MPP is what we call a Pathfinder mission. So this one was launched first with a bunch of instruments, and we eventually launched 2 more, and I think there's like another 2 scheduled for launch. And we're going to be looking mainly at this satellite here. It has an instrument on board called VIIRS, Visible Infrared Imaging Radiometer Suite. It just takes pictures in a bunch of different wavelengths of the Earth. It has daily global coverage. It orbits in the polar orbit, and it has all those bands I was talking about earlier to detect the burned areas, and there's a couple of them in orbit, so there's a lot of coverage every day of the entire Earth. And then notable mentions, other countries have geostationary satellites too, so like the US ones just kind of face, North and South America, but the Japanese have Himawari. Himawari points over like the Pacific, almost into America, and then also like towards Japan and China, Korea. The Chinese have the Fengyang geostationary satellites, which are directly over China, and the Europeans have Meteosat. There's a couple of Meteosats up at a time usually, and those are pointed over Europe and Africa, and some of them are even like over the Middle Eastern region and Russia as well. So there's this ring of geostationary satellites. So what I'm trying to say is that I'm going to be talking about a few satellites here, but there should be global enough coverage to do this kind of study anywhere in the world that you want. All right, so we're going to take a look at some of these fires and burn signatures and list some pros and cons of each sensor. And we'll mostly be looking at the Los Angeles Palisade fires. These happen in January 7th through 31st this year, 2025. And mostly going to be looking at NOAA VIIRS and Sentinel-2 for this case, but we'll look at a bunch of satellites. So the first one, I'll just go ahead and click all this through, is NOAA 20 VIIRS. And I'm going to put some links in the chat. See if I can do this. Okay, grab the chat. Okay, perfect. I'm going to put a couple links in the chat for the first satellite. So that first link, and we'll go over it all together, so no need to worry. The first link is the specs of the satellite, so we're going to see like what bands are on board. And then the second link, it's quite large, but it's this really cool website that NASA has. Oh, the link is slightly too big. Okay, I know what to do. Don't worry. I'll send that link in a bit. So we'll look at the specs of the instrument. Okay, I just want to look at the bands. So VIIRS has these bands on board, and some of them are called like imagery bands, and they're very high resolution, like 375 meters. But we'll be looking at these moderate resolution bands. They're called M bands. These M bands are at like around 750 meter resolution, and there's different, and they go from like 400 nanometers, so that's like ultraviolet blue light, and they go into the infrared, so like 12,000 nanometers. So we'll be looking, so you can construct like a true color image. So you can use like blue, one of these 400 nanometers, green like 555 nanometers, and then the red like 672. And then there's also the veggie band. It's this 865 nanometers, and the reflectance on like the burnt vegetation, that's this 2250 nanometer band. So I believe these are all 750 meter resolution, and that's all the imagery that I've been showing you thus far. Okay, now we're going to go to NASA Worldview, and I'm going to put that link in the chat. I'm going to just go to a fresh NASA Worldview. NASA Worldview. And we're going to load in the data together. Okay, so there's that link. Put that there. Okay, so right now it's showing Modus, but let's load in. You don't have to do it right now with me. You can just watch and just have the link for your reference later. So I'm just going to type in the satellite that I want. I'll show you what I did. I'm in, it has a splash page and it has like a search bar right away, but if you want to add something later, there's this button here called Add Layers. And I'm just going to put NOAA 20. NOAA 20 views. Here's the true reflectance, so it's already loaded on there. Let's just start with that. And you can turn off different layers here. So here's NOAA 20. You can see it's labeled the true color reflectance. And let's go to yesterday. And then let's also load up the orbit so you can see the path of the satellite. So NOAA 20 years orbit. Just NOAA 20. I'm going to click on ascending daytime. So this is the time in UTC, Universal Coordinated Time. So at 2040 UTC yesterday, it passed over California. And you can see the edge of the swath on this line here and on the other side here. The swath is about 3,200 kilometers wide. And it cuts these up into 6-minute sections. So like 6-minute sections, 2045 to 2040 and so on. And you can see the orbits from the whole day that it collected. I think it orbits around 16 times per day, and it captures the entire Earth. And an orbit lasts like 100 minutes, maybe 90, 100 minutes, something like that. Okay, and now let's put on the Dayland Cloudfire RGB. So NOAA 20 years. Here we go, add layers. This is the corrected reflectance bands M11, I2, and I1. They use the higher res bands where possible. I'm going to zoom in here. So this is a Dayland Cloudfire RGBs. This is where the vegetation shows up as green, the desert is brown, the burn scars are red, clouds and snow and ice on the ground are shown in this light blue color, whitish to light blue color. And I'm going to go to one of our analysis dates, which is 2024, August 7th. And here's the park fire. This is the fire that I was showing you earlier in the slides, and you can see it stands out really well in this false color RGB. Here's the front of the fire. This little appendage started to appear in August during the firefighting operations, and the fire actually shows up as this bright orange color. And you can see the smoke. The smoke is this light blue color emanating. So in the blue channel, there's the 0.67 micron band, which is the red band, essentially, or the visible band. And the smoke is scattering a lot of light back into the sensor, so it shows up as blue. For the 2.25 and the 0.86, those are what we call near infrared bands. And they tend to penetrate further into the smoke, so you don't really see like a red or green signal in the smoke. It's mostly blue. Similarly for clouds. Well, clouds are more whitish, so they have a little bit more signal in the other two bands, but they're very blue as well. There's some other major burn scars over here. Not many people live out here though, so these weren't like as famous in the US as like the Park Fire, and as we'll see later, the Palisade fires, which were in Los Angeles. Okay, let's move on. Wait, let me show the hotspot detection. I think that's really cool. So now 20 views. Let's do the hotspot. So all these satellites, they have a channel called the 3.9 or 3.7 micrometer. And they have these fire and thermal anomaly products. If I check it, there are these dots that appear. And when a pixel gets hot enough, it starts emitting a lot of light at 3.7 micrometers, just according to its heat. And we can actually detect fires. And we put these dots, and these dots have like a radius of effect defined by the product, but essentially it just lets you see where the fires are. There are a lot of false alarms from this band because a lot of things can make the 3.7, 3.9 micrometer band light up. But it's cool to see all these dots in the world. There's a lot of fires going on, a lot of what would you call it? Like maybe biomass burning, like controlled burns. There's people just burning fires. Like little tiny signals can trigger this. There's a lot in Africa. Yeah, I use this product to find test cases and confirm fires. I think it's really cool. Okay, let's see what else we got. Right, so that was a polar orbiting satellite. It's a passive sensor, moderate resolution, global daily coverage. So what's nice about that is you can actually see a lot of important fires with the moderate resolution. It's good enough. And the global daily coverage means you can make daily maps anywhere in the world, as long as there's not too many clouds. And I'll go over what you do with clouds later. Let's look at Sentinel-2 real quick. I'll put these links. Sentinel-2, let's see, Copernicus browser. This is the web viewer that the Europeans use. So I showed you the NASA one, which is like a US one. And then Copernicus is a satellite program in Europe. All right, cool. That one sends. So let's go to Sentinel-2. So this is just like a little page about it. Actually on NASA, a lot of these missions are joint missions between like NASA and other countries themselves. So a lot of times they'll be cross-referenced. So Sentinel-2 is kind of like NOAA, except it's way higher resolution. So spatial resolution, you can see 60 meters, 10 meters, 20 meters, about there. We just looked at 750 meter, 375 meter imagery. It has a lot of similar bands. It's got all these blue ultraviolet bands, green, red, some near infrared. Here's the veggie band, and here's the burned area band that I was talking about, this 2,200 and 2 nanometers. So a lot of satellites, they don't have the exact wavelengths replicated because they all have slightly different missions and purposes and design requirements and manufacturers and all that and all this stuff. And people fight about where the bands should be centered, and because people have different projects and different research studies. But as long as you have a band around 2,200 nanometers, you're going to find, and like 860 nanometers and 664 nanometers. These are very common bands. A lot of missions have these, like including Landsat and like a billion other missions. Let's see, anything else interesting? Nah. Okay. So let's go to the Copernicus browser link now. So we're going to look at the imagery here, and the Palisade fires show up really nice. I know I showed the Park fire before. I'll go back and show the Palisade fire on Veers because it is interesting. So everything should be preloaded. The first time you hit the link, it might say if you want to make an account or use anonymously, just use it anonymously. I find that the European websites always let you do that, which is nice. You don't have to create an account. So this is Los Angeles, California. So I'm gonna zoom out real quick. This is where we are. We're in Southern California. This is LA, and just outside the city, there's a bunch of houses here actually. And this red area, this is the same false color imagery that we've been seeing, but now at 10-meter resolution. So we can zoom in quite a lot. See that data is loading. And this is over here, 2025, January 12th. I think the fires were burning on the 7th. And I've selected, there's like they have like they just call it like wildfire or something, this color, this false color image. And you can see it's very mountainous here, and there's a very well-defined burned area. This particular fire ended up burning thousands of people's homes in the mountains. And if you saw the news, they were like flying in planes from Canada and Mexico, including our own, just dropping water over these mountains continuously. And I think this event was from like the 7th to like the 31st of January. So it was quite a long and devastating event in a populated area. And you can see it really well in Sentinel-2. So firefighters receive information from satellites like Sentinel-2, which are really high resolution, a lot to find the perimeter of these fires and like where it's being affected. They fly planes, of course. They have drones. It's quite a large operation, and this is like one key component. And then after the fire, these burned area maps are generated for like research purposes and forecasting purposes. So in the news, even they were talking about how you would think rain would be a good way to put these fires out, but actually because there's inclined terrain here and these burned areas, it would actually cause even more devastation with the debris flows and the flash flooding. So there's a lot of like risk mitigation, like the emergency managers of the city are figuring out where to send, emergency services like paramedics and firefighters. Let me see if I can zoom out and show some of the coverage of Sentinel-2. It has a much thinner swath, so like the coverage is pretty poor. Yeah, so here's the width of the orbit. If you remember, Veers had much. They still have it up. Yeah, I'll try and put Veers up. Here's the Palisade fires for Veers. Yeah, so it's a lot worse resolution. You kind of can't tell what's going on. You can still tell it's there. But you get daily coverage of this fire using this satellite, and then with this satellite, you might get a pass like every week or two. But it's a lot more higher quality data. So you can see it's a really skinny swath, and as it's orbiting the Earth, there's going to be huge gaps in the coverage. So your revisit times are pretty poor. But with yeah, I can see I can just scroll every day. So this is January 11th, January 12th, 13, 14, 15, 16, 17. You can see sometimes there's clouds and smoke from this fire over here, for example. So some days it's cloudy, but you can kind of like, you can get a map of how this evolves daily, which is really nice capability of these moderate resolution imagers. And then I'll show you, there's like a calendar with the availability of imagery for this location. So I'm going to zoom in, just show you the revisit time potentially. So we're on the 12th, 14th. I wonder if there's like an overlap or something. So there's two Sentinel-2s, and they're offset in the orbit. So sometimes you can get a little bit more coverage. Just want to see what loads up just to show you. Yeah, so on the 14th, 2 days later, the swath has migrated to the east. So you're not getting the Palisade fire anymore, which is over here. Okay, so just a summary on Sentinel-2. So Sentinel-2 is a polar orbiting passive sensor. It's super high resolution, 10 to 20 meters. For a lot of the bands, I think somewhere 60. It has a poor revisit rate. I think it's like 1 week with both satellites in orbit, and like 2 weeks, about 2 weeks or something like that with just one satellite. Okay, let's talk about geostationary satellite now. So we're gonna do GOES 18, which is GOES West, which is the geostationary satellite over the Western US. We'll put these links in the chat. That's the fact sheet, and then this is the link to another viewer for geostationary data. We'll go over that. Okay, so there's a quick guide on all the bands. So there's like PDF files. It looks like there's even Spanish and French versions, which is super cool. And the satellite is called GOES 18, but the instrument we're going to look at is called ABI. ABI stands for Advanced Baseline Imager. And it has like these central wavelengths and micrometers. And there's some nicknames for the bands to tell you what they do. So like blue, red. Here's the veggie band, so we're going to use that. Some Cirrus bands, Cirrus cloud detection. 2.2 micrometers, we're going to use that. A lot of times it's called cloud particle size because turns out that cloud particles, depending on their size, will scatter different amounts of light. So it can tell you about like the microphysics of the cloud that you're looking at, but it's also good for burned area detection. So we'll use that. It's got a 3.9 micrometer band, so fires emit the peak emission of a fire according to its temperature is around 3.9 micrometers. So you can detect fire pixels with fire in them. It's got some water vapor bands, and the mid infrared is 6, 7, 8, 9. 10 is the window IR channel, so you can see the temperature of the surface of the ocean or the surface of the land. If there's no clouds, if there's clouds, you can see the temperature of clouds, storms, stuff like that, and so on. So it has a bunch of cool bands. let's go to Cirrus Slider now. That's that next link I sent. This website doesn't archive to my knowledge. It just has like kind of real-time stuff. So you can select the satellite here. It's on GO 16. We want GOES 18. And then I'm just going to stop this, go to the end, because it's still early in the morning on the West Coast, so it's pretty dark. Yeah, so I don't know if there's any fires to zoom in, maybe in Canada or something. Let's look around. It looks like there's some smoke here. I don't know if this is the fire here. It's really hard to do detection using GOES, but it's really, really nice. And I'm gonna play the animation and explain why. So if I play this animation, you can see that over time the clouds are moving. I'm gonna move to 19 just because it's daytime over there. Let's just look here. So you can see how the clouds move over each. It's going every 10 minutes. This is every 16. We can go every 10. So you can see the clouds moving. See over land. And let's say a polar satellite gets like a still image of the day of the Earth, essentially, like kind of. And there's cloud covering your burned area. So that day you're not going to be able to see the burned area. But with the 10-minute imagery, the clouds eventually move, with the fronts, with the air masses and so on. So maybe like if there was a burn scar like behind this cloud, in 20 minutes you can see it. So there's a lot of like combined approaches to change detection over land. For example, your best quality data is going to come from your high resolution imagers, but they're not always available. Moderate resolution imagers are always available, but they may be cloudy. Same with the high res, may be cloudy. And then these geostationary imagers, they're very poor resolution comparatively. But if you have clouds in the way, you just got to wait like 20 minutes and then you can see it. And this is important for firefighting operations. So detecting the fire, mapping the burned areas, and then for forecasting, using those burned area maps, because right after the fire burns, it's susceptible to debris flows from rain events. So early detection is very important, and we can use these different orbits to maximize our coverage in time and space and resolution with the different instruments. And this website's really cool. There's like different views of the satellites. And it's got Himawari. I don't know if the Himawari is working or anything, but it's got a bunch of satellites here, Meteosat, Himawari, and there's quite a lot of products. So was using the Dayland Cloudfire RGB, but there's tons of false color imagery, bands, fire type of products. So I use this website quite a lot to find test cases and just look at current weather events. Right, so that goes to geostationary orbit. Go back here. Geostationary orbit, passive sensor. That's partial global coverage, but a lot of the countries have satellites in the geo ring. So if you're in Europe, Africa, or maybe like closer to Japan, there's going to be coverage for you. There's usually, at least over the US, there's 1-minute scans over special areas, 5-minute scans of the US, and 10-minute scans of like all of like North, Central, and South America. And the bands go from 0.5 to 2 kilometer resolution. And as the further you get away from the equator, this can degrade to like 10 kilometers, in which case you might want to use polar satellites. Okay, the last satellite I want to talk about is Sentinel-1. It's a synthetic aperture radar. And let me just skip to how this works because it's It's a lot more complicated. It's not like it's not like an easy camera. Um, it's an active radar remote sensing technique, where the satellite sends its own pulse, its own signal. It's got a transmitter, and then the light, like the signal that bounces back, is measured by a receiver on board the satellite. And that backscatter um, has been modified by the terrain, it's been modified by the atmosphere in the clouds. So that backscatter shows like a signal of what it's sensing. So the way you can do change detection with a radar, because it doesn't take an image, right? So if you look at this radar image, it's like not intuitive at all. You can kind of see the surface and you can kind of see some stuff, but it's really noisy. I'll show you some images in a bit, and it doesn't make so much sense. So the way we do change detection is by differencing the phase, like the wave phase of two images, and this is called interferometry. So I'll just read this bullet point. Interferometrically combines synthetic aperture radar images to infer changes in line of sight distance between the satellite and the ground. Okay, so what does this mean? So I'll explain this diagram. Here's the satellite. It's in a polar orbit. It's coming over the Earth. It shoots a signal, and then it receives the backscatter from that signal, and it's been attenuated by the ground. It's called attenuation. So in pass one, the backscatter has a phase, has like a phase X, right? And then pass two, this may be like a week or two later, right? When the satellite revisits this area, it'll have another phase. And they'll be off in phase the amount that the surface has changed in the orientation of the pulse that was sent to it. So what does that mean? Simply, I'm going to keep it simple. If we imagine here on the right, this black line is pass one, and the dotted line is pass two, just like right here. The phase can be slightly off. It can be more off and more off and more off and more off until it's like a whole period. This be half a period off. And it turns out this phase difference is directly correlated and related to the amount that the surface has changed. So if the surface went like up or down, some kind of deformation, we can detect it through a phase change between two passes. And if we color code the distance of the phase change, so for this type of satellite, 0 centimeters to 2.3 centimeters, we can create an image of the deformation of the ground. And these images look like this. They're very colorful and have like a lot of like layers to them. These are typically used for earthquakes. So after earthquakes, there's like obviously there's going to be like these ripples in the ground and all these deformations. So this is like change detection in general. You can do this interferometric technique for change detection. And you can see these high gradients here where there's a lot of change very rapidly in the surface. I think this is like some epicenter of like an earthquake. But turns out we can also use this to infer burned areas, because after the vegetation is burned, the land gets deformed, the backscatter changes, the phase changes. So if you have a pre-fire scan and a post-fire scan, and the only thing that happened between those two images is a fire, then you can infer burned areas. So that's what my colleague did. Dr. Roger Michaelitis. There's his email. He has some papers. Yeah, I think he has a paper out on this if you search his name and synthetic aperture radar. On the right is that false color image I was showing of Sentinel. This is Landsat, which is a similar instrument to Sentinel-2. It's a US mission. Also like was it 10, 30 meters, very high resolution, something like that. 60 meters, something like that, yeah. So here's a burned area in red, and this is a synthetic aperture radar image. So I think it's might be the amplitude or something in the back of the radar. And this quantity is the unwrapped interferometric phase in radians. So excuse the color scale, but 0 is white, negative is blue, positive is red, and we're able to delineate with similar, even better resolution than these high resolution passive imagers, these burned areas. Which is really cool. And what's very, very cool about this technique is that, especially for these like low cumulus clouds that we're seeing in Landsat, for example, the radar will penetrate straight through the clouds, and so will the backscatter. This is true for smoke as well. The only time the signal gets affected by clouds is like during like thunderstorms where there's a bunch of ice in the cloud. So if there's a bunch of ice production in the cloud, it will tend to block the radar signal. Otherwise, you can kind of see straight through. So it's kind of another way to get more real-time and high-res information for firefighting and forecasting applications. Okay, so now I'm going to go back real quick. And we're going to look at some imagery. So I'm going to put the fact sheet in the chat. Oh, thanks, Joel. I didn't see the chat about these fires in southern Utah. Okay, there's the fact sheet. And then after we'll look at it in the Copernicus browser again. I want you to see the imagery so you know what I'm talking about, but it's kind of like useless unless you process it for burned area applications. It's useful for other stuff like flooding. Okay, so Sentinel-1 SAR. Gonna hit that link. So this just tells you all about the mission. I believe it's a C-band SAR. So there's different wavelengths that they're sending these pulses at, and the wavelengths are sensitive to features of different sizes. I think the C-band is sensitive to like 8 centimeter sized phenomenon. You can see in gigahertz if you're familiar with radar. 5.4 gigahertz is the frequency that it's using, and it has different scan modes. And I think there's some pictures of the scan modes down, but some of them have 5 meter spatial resolution. And this one has an 80-kilometer swath, so very narrow swaths. There's other modes with larger swaths, and this one is 5 by 20 meter resolution, 400-kilometer swath, which is quite large. But you take a resolution penalty of 25 by 100 meters. And so on. And these are orbiting the poles, 98.2 degrees, essentially. Let's see some images of the orbit. I think they had a couple. That's cool, that's the instrument. So synthetic aperture radars have like an antenna, and they like do some math to make the antenna longer and like mathematically, and it gives you like a lot better resolution than other types of sensors. Let's see if I can find the image. Here's like a cool image of the orbits. You can see kind of like what the coverage is. Something interesting about synthetic aperture radars is they're active. They're not passive, so they have power draw. And what that means is that they're not always on. They need to be tasked a lot of the time. So the power draw is so great that in advance you need to know where you want to turn it on. And I don't even yeah, they're turned on over the oceans. They're usually used to detect sea ice, actually. They get insane backscatter for sea ice and seaband SARs. So a lot of mapping of that for ships and like for fishing and commercial purposes, national security and so on. There's some images there. I want to see the scan modes. Here are the scan modes. So it's a side-looking instrument. So it turns out that, you know, for a bunch of applications, the backscatter is better than the side. So that the satellite is traveling this way around the Earth in the along track direction, and it's scanning like this. It sends the beam, it sends pulses down, and there's different scan modes that are going on. And the different scan modes are different resolutions. And the reason you would use one scan mode over the other depends on like what you're trying to sense. And these scan modes are uh, chosen in advance for what you're trying to sense for the region of interest, and they're polarized. So that's what this HH, HV, VV, VH. So that would be like a quad pole measurement. So if you polarize the light signal that you send out, um, that would be like H, and then you receive backscatter, and maybe the polarization has changed. And you can even it'll send out like a horizontally polarized pulse and a vertically polarized pulse, and it'll sense the horizontal and vertical components that were backscattered. And you can mix and match what you send and what you sense and what you receive at the sensor and the angles and all these things. And the backscatter can tell you a lot of information about like um, the deformation of ocean surface waves and sea ice and burned area, as we saw. Okay, let's look at it in the Copernicus browser. I think this should work. We're over the Palisade fires again. So the products are quite complicated to like interpret, but I just pulled up this that just have an RGB ratio, and it combines the VV VH polarizations and the gamma zero into a false color visualization. So here's LA. Um, it has some stuff about like what the different colors uh, end up meaning. And so it shows water areas in dark red or black, urban areas in yellow, vegetated areas in turquoise, um, and what was the last thing? And bare ground in dark purple. So bare ground could be desert. This is, I can't see the date on this image, but yeah, this is basically what it looks like. It's very high resolution. You can see quite a lot of details from urban landscapes. Uh, the mountains have like quite big angles in them, so it has lots of contrasting backscatter, so you can see the shape of the terrain really well. In the same vein as this, and the water's pretty flat unless there's a lot of waves, wind stress. Yeah, so we can look at a raw image. There's like a non-RGB image of it's a VH mode, it's a send out vertical, receive horizontal, I believe. Yeah, and this is, okay, good, 2025, January 9th. Let's go to a pre-fire date. We can see if it changes. Oh, it actually did change a little bit. Zoom in. Go to back to the ninth. It's hard to tell. Maybe there's a little bit of a signal change in the mountains. But there's quite a lot of processing that goes into making the burned area map from the SAR imagery. And interferometric imagery is not like readily available in web viewers because you have to choose like a pre and a post and then do the interferometric process, which is computationally intensive. So it's not as simple as just like, hey, here's what the satellite, like what we're operationally processing right now. There would be infinite permutations of interferometric phases you could do. So it's just, I don't think it's available on any web viewer. Something you have to do manually. Okay. So it's a polar orbit, active sensor, super high resolution, 5 to 100 meters, depending on scan modes and such. Poor revisit rates, depending on how many you have in orbit, it could be like a week or two before you see the same exact spot again. And they need to be tasked, so they're not always on due to power requirements. We went over that. Here's one final test case I'll show from SAR. So this is like the same burn scar we saw earlier from here, but I think this is advanced, like a couple of weeks. And Dr. Roger Michaelitis put like this proxy to soil burn severity map. And I just want to show this is what it looks like in virs. So this is the 750 meter res. And I forget what resolution this is, between 5 and 100 meters, but it's a lot more finer detail. Let's say on this day on virs, you have these clouds blocking the signal, and then in the SAR, we can just penetrate straight through those clouds. Okay, looks like there is a 10-minute break. So it is 10:10 Eastern right now. All right, everybody, we're back. I hope the first part of the session was nice. It's definitely a lot of information. We're gonna look at some burned area data sets now. So some more processed maps of the burned areas. Just give me a second here. Okie dokie. So these are burned area data sets that are created in the United States of America. So unfortunately, these aren't produced outside of the US, or maybe your country may produce these in some form or fashion, but I'm going to go over for the United States. Maybe it'll inspire you at your organization to create these actually. I want to talk about the debris flow hazard map. So this is made by the United States Geological Survey, and it's a product called the Emergency Assessment of Post-Fire Debris Flow Hazards. It's created and updated about 2 to 8 weeks after the ignition, when the fire is 80% contained by firefighters. And the reason for this, first of all, the fire's growing before it's contained at that point. So making the map, it takes some time, so there's that aspect. But it's also generated using Landsat data, surely Sentinel-2 as well. So you need a pass, could take a week or two to get a cloud-free pass. It could take longer. And there's also in situ measurements of burnt matter. So they have to go into the burned area. So it needs to be somewhat contained, 80% at least. They go in there, they collect soil samples, and with the satellite data and that and some other stuff, they have a debris flow model, which I'm going to show you in a second. And the map shows you probabilities of debris flows or like flash flooding, given a certain amount of rain over that area for a particular fire. So like their criteria is 24 millimeters per hour of rain for 15 minutes. And then it gives you a probability of debris flow. They found, I had to talk to the scientists that developed this product, one of them, Jason Keene at the United States Geological Survey. And he said the best predictors for this flood model for burned areas is a difference normalized burn ratio and the slope of the terrain. So we talked about normalized burn ratio. Difference is it's very simple. There's a lot of indices like this. It's just like you subtract the pre-fire and the post-fire normalized burn ratio. That's it. So you need two images, a pre and a post-fire image. And right, the other variable, the slope of the terrain. So the more slope you have, the more force from gravity you have to accelerate the water down the side of the mountain. The more component of that force. And then we'll also look at a data set which is even higher quality, but it comes out like 1 to 2 years after the burn date. It's called Monitoring Trends in Burn Severity. I think it's also the USGS or Forest Service. We'll take a look in a second. They're like the highest quality burn severity maps. If you were to want to train like an AI model or find some good test cases, this is where you would this is where this map comes into play. The previous map is for forecasting applications, and it also like it sticks around forever. But like it has like the better, latency, just 2 to 8 weeks, something like that. We're monitoring trends in burn severity, 1 to 2 years. Sentinel-2 plus Landsat, and it's a US data set, and it goes back to 1984. And I think the last update is 2023 fires. Okay, so I'm gonna open the chat here, and I'm gonna put this link in there. We're gonna look at emergency assessment of post-fire hazard debris flows first. All right. Let's see. Okay, so there's like some options you can have here. Maybe first let's go to this link here. They have like a National Weather Service like little guide to how to interpret the product and why these burned areas are causing debris flows. That's in similar cartoons to what I showed, and some write-ups, some test cases, a bunch of resources for forecasters. So if you want to learn more about debris flow forecasting for burned areas, you can check out this PDF. They have linked here. And then they have all the fires here. I don't know exactly which ones, but you can select a fire year. So we can do 2025. And they have, in the US, at least, we name the fires. They have names, kind of like a hurricane or something, I suppose. So Palisades. And then it shows you the basin that was burnt. On a nice map here, you can see the terrain. You can see some flow channels. And these are what's showing is the probability or the likelihoods of flooding. And it gives the criteria here, like a peak 15-minute rainfall was used to make this result. So after this map comes out, it's no longer updated. So as the as the burn scar ages, it will recover over time. Um, Actually, let me show that. Um, I'm back in NASA Worldview if you're curious. Um, but I want to show how a burn scar recovers real quick. I think it's the 10th. I want to show the Dixie Fire, and I want to show how intense it is. So here's the Dixie Fire. You go to September. There's less. Yeah, there you go. So you can see the Dixie Fire is 2021, September 17th. Has a very strong signal in the Dayland Cloudfire RGB. You can see there's a bunch of vegetation around here, and it burned all of it. If we go like 2 months back, there's a bunch of vegetation here. There's not much going on. This fire burned for months. It was quite an intense fire. So here's like the landscape before September. There's during the fire, and then I can change the year. So 2022. Let's do a cloud-free day. You can see the signal is already weaker. There's some vegetation regrowth that's occurring. Go to 2023. Let's go to 2024. Yeah, here's the park fire that we analyzed, and we talked about how the Dixie Fire was having a weaker and weaker signal here. So yeah, it's essentially what's going on. So these burn scars age, and this data set doesn't show that. It's a topic of research, and actually, a couple of scientists responsible for this product wrote a paper on the recovery of these burned areas and their impact on flash flooding. And we're going to do a paper analysis after we look at these two products. So we can also look at the park fire. So that burned in 2024. Select fire, search park, and here it is. So they've mapped it all out. They use satellite data, in situ measurements. They ran it through their debris flow model, and they made these probabilities. Probably if you look through here, they should have a paper on this. You can look up their methodology on how they produce this. Maybe if it's not available in your home country, you could reproduce this as well. Okay, let's look at the monitoring trends in burn severity data set. And I will put that link in the chat. I think I might just search it. Monitoring trends in burn severity. MTBS interactive viewer. See if that works. If it's not working, that's fine. I think I have some images of it. Maybe their homepage is working. Okay, cool. So here it is. You can download the data. It's available in GeoTIFFs. So if you want like a direct download, you can choose like the date ranges you want, and I think it's got like these like GeoPandas polygons, and you can look at the area of the fires, and they got burn severity, high quality burn severity maps, and so on. See if the interactive viewer. Come on. It's similar to all the viewers we've been seeing. There's a map, there's polygons of the fires. The polygons are objects that you can click on, and it tells you how much of the fire has, how many acres it burned, and some other details about the fire. I think it even classifies it as like a wildfire versus like a controlled burn. And I may be wrong about this, but it might tell you if it was like caused by a person. So something important about wildfires is that I think like half of them are caused by lightning, and then half of them are caused by accidental arson, like some kind of event, some kind of spark or campfire, cigarette butt, so something like that. Okay, so I think we'll just move on from that. I think I have an image at the end of my slides. I'll show that. Yeah, it looks like this. It's this bottom left image. So here's the Dixie Fire. We've been looking at it a lot. It's got like burn severity there. And here's the August complex. So it's a really nice resolution. This also doesn't age with time. It's never updated. The website shows the methodology, how they produce these maps. I think they have a paper on those. Yeah, and it goes back to 1984. It's a really nice data set if you want to train some models. Okay, let's do the paper review. I'm going to put the link for this paper in the chat so you have it as well. It should be open source. It's an AGU paper. Okay. So this is a paper by Grabber, Thomas, and Keene, 2023. Let's just go to the paper. It's called How Long Do Runoff-Generated Debris Flow Hazards Persist After a Wildfire? I'm going to open it up in the PDF. And it goes into like a bunch of background of the debris flows and why they're doing this. And they basically want to find out how long it takes for a fire to recover and how can we detect this from satellites in like a reasonable amount of time and get this information out to the forecasters in some kind of future product that would be possible. So they use the MODIS leaf area index. And the leaf area index is a very complicated quantity, but it just tells you about essentially how much vegetation is in a pixel based off some scattering properties of vegetation and what's going on in the scene. And so higher leaf area index is more vegetation, lower is less vegetation, essentially. That's all you need to know. And what they did is they said, okay, so if there's a fire, leaf area index should go down. And when the vegetation regrows, it should go back up. And of course, there's going to be seasonal variations of leaf area index. So in the late summer into winter, it's going to be very low because it's dry, it's cold. Everything's going to die off anyway. And then in the spring into the summer, it's going to be really wet and warm, and there's going to be a lot of sun, so the vegetation should peak again. So first we'll look at this bigger graph. On the y-axis is the leaf area index. And on the x-axis is the year, and then there's this line that's finer scale than a year. It's probably the 8-day binning. And you can see that leaf area index, like, at the start of the year, it's like winter in the northern hemisphere. And then we get into the spring, summer, the leaf area index peaks, and then it falls again into the, fall, winter. And yeah, so there's like these peaks and valleys according to the seasons. And you could probably get like a climate signal out of this if you looked at it for enough years. And here, for this particular area, they're looking at a fire. And the leaf area index suddenly drops way below 1. Stays there for a little bit because it's winter. And then there's some regrowth. And that regrowth peaks way lower than all the rest. So this area, for example, is like it's trying to recover, but it hasn't recovered to its pre-fire vegetative state. So fire happened in 2018, around the beginning of 2018, end of 2017. Leaf area index is very low. It recovers a little bit into the spring and summer. Seasonal changes lower the LAI again. And then the next year, it's back to its previous LAI levels, maybe even higher. Um, so this is like an interesting way to look at recovery due to vegetation regrowth. It doesn't tell the whole story because if you have a devastating fire, it could take away all of like the giant trees and root systems and like just the biodiversity of vegetation that was anchoring the soil before. And now you have all this new growth that isn't of the same quality might be the wrong word, but it's not the same kind of vegetation that was there before. So there's that caveat, but we can see regrowth and um, to kind of adjust for all of that, they made this recovery ratio. So in a local amount of time, let's say like 8 days, they'll take the LAI average for that 8 day time period, and then they divide it by the LAI leaf area index of the same time interval, but 5 years previous to the fire. So that's what this graph is. So on the y-axis is the recovery ratio, and on the x-axis is the years. So I think we're looking at the same fire here, this 2018 fire. And these are the different seasons. So winter, these colors, the blue is winter, green is spring, summer, fall for this year. And you can see the recovery ratio is increasing. This is the seasonal line. So there's different averaging intervals they looked at. So there's 1, 2, 3, 4 points per seasonal. So that's like every 3 months. And there's a monthly average so there's 12 points between these two time steps. And then there's an 8 day line, which has a lot more variability. But you can see they actually follow the seasonal trend pretty well. And the result of the paper, they analyzed quite a few fires, and they had flash flood events associated with the fires, and they were able to come up with like some summary statistics that show that after the fire, the recovery ratio, once it's about 2/3, there's a significant decrease in debris flows after that. For some fires, the recovery ratio, it only has to be 0.5. For some, it needs to be closer to 0.7. But they found like, 0.6-ish, 0.7-ish. Most fires have recovered. I think there's another figure. Yeah, this figure. So not all fires recover within a year. Some take multiple years. This graph is quite complicated, but on the y-axis, it's the name of all the fires, and then there's different sections. Year 1, year 2, year 3, which is the x-axis, time since fire ignition days, and these red dots is when there was a debris flow observed. So this monument fire had 3 debris flow, I think 3 or 4 debris flow events in year 1, and in year 2 was the first month with recovery ratio greater than 2/3. And then there was no debris flows measured after that. And they did that for all these fires. You can see this monument fire seemed to recover within year 1. So it's Schultz and Thomas. This Pinal one didn't quite meet that threshold, so they have a 2/3 recovery ratio, but they had debris flow in year 3, and so on. Okay, I'm going to go back to the slides. So the key point is burned land is immediately susceptible to debris flows. The soil becomes hydrophobic. The vegetation that was anchoring the soil is no longer there. There's mountainous terrain with an incline, so there's a stronger component of gravity pulling the water down. Forecasters want to know about this. And over time, these burned areas, they stay there. There's new ones, they age, they recover. How do we sense that? They can stay susceptible to debris flows for up to 5 years, depending on the recovery time. I think most of them between 1 and 3 years. So that's important. Like a forecaster should like have this background, and they may even have a product to show them leaf area index recovery. And maybe that's something I'll work on in the future, for example, or that you could work on. And if forecasters can see this, then they can accurately send out flash flood warnings in areas with burn scars. And we saw some highly populated areas with burn scars in Los Angeles, where they do get rain events. So the paper we saw, leaf area index from polar orbiting satellites, is shown to be a good indicator for vegetation recovery. So they used MODIS. MODIS is the mission's ended. It's like not, I don't think it's operational anymore. It's like it's been put into a different orbit. I think you can still get data from it though. But VIIRS, NOAA 20 and NOAA 21 VIIRS have leaf area index. It's produced like every week, I think, like every 7 or 8 days. Takes a bunch of passes, takes out all the clouds, then it calculates leaf area index. So you could just make this product and see if it's of any value to forecasting. So the authors found when burned land reaches 2/3 of the 5-year pre-fire leaf area index, susceptibility to debris flow is greatly reduced. In most cases, the recovery was between 1 and 3 years. Here's the same graph again. We were going to analyze it here, but I think the paper was better. Okay, we're going to switch gears. We're going to talk about the structure a little bit of the National Weather Service in the United States and how it relates to this debris flow and like forecasting stuff. And then we're going to move on to a coding exercise and then like issue a product, like a flash flood product at the end, and I'll explain everything. So the Weather Prediction Center is the one I want to focus on, and then we'll move towards the weather forecast offices. So in the U.S. and NOAA, there's a bunch of national centers, each responsible for different types of weather. So the National Hurricane Center is in Miami, Florida, and they do all the prediction for hurricanes in and around the United States. Storm Prediction Center issues watches for tornadoes and severe thunderstorms. They have probabilistic outlooks for hail, tornadoes, and wind. Aviation Weather Center, they cater towards the airlines and anyone who's flying, like what kind of significant weather would affect them, cloud top heights, thunderstorms, turbulence. Climate Prediction Center does outlooks on the seasonal to subseasonal scale of like temperature and moisture and other stuff like that. Environmental Modeling Center, they're like figuring out how to assimilate data into the models and a bunch of other stuff regarding numerical weather prediction. Ocean Prediction Center is responsible for the Atlantic and Pacific Oceans in the Northern Hemisphere, just for commercial boats and also near the coast even. And they're looking at lightning, convection, wave heights, strong winds, stuff that may disrupt commercial traffic and worldwide trade. And so I guess the last one is the Weather Prediction Center. It's listed right here. So the Weather Prediction Center, they do this special product, which I'll show in a second. It's mesoscale precipitation discussion. And in the 0 to 6 hour time frame, they'll issue flash flood warnings as needed all over the US. And they also do all kinds of excessive rainfall outlooks. If it has to do with water falling on the US, they're going to issue some kind of national product, and the weather forecast offices and other stakeholders will look at it, and they can issue like finer warnings, talk to emergency managers, and so on. These are the weather forecast offices. So each like colored area has a bunch of counties in it, and these counties warning areas are the responsibility of that office. I think there's like 120 something local forecast offices in the United States. So I'm here in Dallas. Sterling, if you're in DC, Maryland area, and so on. The function and purpose of the weather forecast offices has changed like over the decades. But one thing they focus on is information decision support services. So they're in constant contact with like emergency managers from all the cities in their warning areas, and they're getting like fine scale updates of what's going on and what's going to happen in the near future. So if there's an event coming up, like a 5K, and it's going to be like 100 degrees, the organizers, they may have to figure out how to get emergency services and water and whatever else they need if they cross like certain temperature thresholds. Stuff like if there's lightning, they might need to cancel the event. It might be like a marathon where like there's like 15,000 people plus everyone spectating or whatever. As well for like severe weather events that are going to impact the area. Like, is there going to be a huge snowstorm? Do they need to like import millions of pounds of salt for the roads? And is there going to be a hailstorm? Do they need to like relocate all the construction equipment and cop cars and stuff in the city to a safe place? The fires. So fire weather. How's the fuel looking? Is everything dry? Is there going to be like a lightning event? They're monitoring satellites, seeing if there's any fires in remote areas that might not have been detected yet on the ground. Anything like that. So they serve a very important role. They like connect a lot of these products to everyone in the US, for example. So at the NOAA Weather Prediction Center, I used to work there, so this is where I got this idea. And there's this product called the Mesoscale Precipitation Discussion. And they basically get to put any background information they want. So here they have like some satellite imagery showing clouds. I think they have some CAPE contours, that's convective available potential energy. You can see some clouds, some cumulus clouds going up. So there's like this rain event that's happening. There's energy in the atmosphere. And they have this pink squiggly line denoting an area of flash flooding possible. This is in New Mexico. It's right next to Texas. I'm like over here talking to you. And they have these burn scars that they've inlaid, I think from the USGS maps we were looking at. And they've hand-drawn these polygons in there. And in part of their discussion, they highlight, and it says, these type of amounts over burn scars across northern New Mexico and southern Colorado, as well as other sensitive locations where flash flood guidance is low. So 1.5 inches of rain within an hour will cause flash flooding. But since there's burn scars here, it could be much more devastating. It could lead to quick runoff and flash flooding. So having these maps readily available to forecasters, updated, near real time, and showing how the burn scars are recovered is very important because they'll issue warnings on this. And the emergency managers of the cities, they'll figure out like, hey, what do we need to do? Do we need to close these roads? Do we need to tell people to to evacuate if they live on like the side of the mountain and it's going to like destroy their house. There's going to be a landslide, so something like that. It could be a very impactful event. Um, yeah, I guess let's do another 10-minute break because I think we have the coding activity after, and that's going to be like very labor intensive. Yeah, so let's come back at what would it be, 11:03 Eastern?
So, Javier, would you like to answer questions now or after we return from break?
We could do some questions now. There's been quite a lot of material.
There are a couple in Q&A for you.
Is that in the chat?
Down at the bottom, there'd be a Q&A button. It might be under the More selection.
Oh, I see it. Okay. What satellite, I'm in the Q&A for anyone wondering, what satellite tools and data are used to create the USGS post-fire debris flow hazard assessment viewer? Yes, they use Landsat and Sentinel-2. They have the high resolution imagers and they have the in situ soil measurements. So the satellite data, they're using difference normalized burn ratio. That's what they're looking at. So they have a pre-fire image and a post-fire image. They subtract them. That pretty much gets the perimeter of the fire. That's done manually, not automatically. So they choose like a pre-date and a post-date. And then once the fire is 80% contained, they go and they get soil samples and they have some burn severity metric. And then that's put into the debris flow model. They say, hey, let's look at the incline of the slope in that area. So they'll use like digital elevation models from satellites like Aster or something. Like there's probably a lot of good data sets to see the height of the terrain at any particular point. And yeah, they use all that data, and there's probably a paper on it. I could probably look for it and then put it in the chat. There's another question. Numerous international satellites you mentioned. How accessible are their data online? Do you have an example of non-US and maybe some non-EU portal viewers? I do not have examples. I'm not aware of any. If someone else is aware, feel free to share. The polar satellites are global coverage. So if you look at any of these viewers, you can see your region just fine. For like Himawari, I don't know if they have a viewer. I think on the Sierra Slider, you could probably look at Himawari Meteosat on Sierra Slider. Yeah, for the EU portal viewer, I think they have one. I think it's called EUMETSAT. I can look for that. It shows the Meteosat satellites and a bunch of their polar orbiters. They have really good global coverage. So if you're in Africa or Middle East, getting into Asia, you'll have some good coverage there as well. And then with GOES, Meteosat, and Himawari, you can basically see most of the oceans. I think the Indian Ocean might be undersampled. Okay, thanks, Megan. You put a Himawari viewer in the chat. Let's see if I can find that one paper. What the EUMETSAT viewer? UMET view, that's what it's called. I'll put this in the chat. I know this one's EU, but It's got some non-EU coverage. And I think they have 2 satellites at least. So
Hello, this is Bill Schobert. Can you hear me?
yes, Bill.
Yeah, the Europeans have a very strong fire weather, and they love to talk about it. So it might be if somebody's interested in that area of the world, that just I can certainly help track down a point of contact if that's needed. But uh, I've seen their briefings, been to UMEDSAC conferences, and they have a pretty strong fire weather program over there using our satellites as well.
Thank you, Bill. Look at that USGS paper real quick. So Megan, are we in break then, or?
Sure. If you'd like to start break, we can come back at 11:10 Eastern or 15:10 UTC.
Yeah, let's do that.
Okay, sounds great.
Welcome back. Welcome back. We are going to do a coding exercise. I have pasted the instructions into the chat, and I'm going to go over them. And during this coding exercise, we're gonna download some data from the NASA LAD stack from VIIRS. And then I prepared a IPython notebook, if you've ever used Jupyter Notebook. And we're going to use Google Colab. So if you have a Gmail account, you can actually access this application called Google Colab. And you don't have to install any libraries. You don't have to install Python or anything. It's all in the cloud and for free if you have a Gmail account. Free in quotes, right? We're going to upload the notebook. I'll go through the code with all of you, and I'll go through how to download this data. So please follow along if you're interested in this kind of satellite analysis and you want to learn how to manipulate data in Python. We're going to look at some burn scars, and then we're going to issue a product, just like the weather prediction product that I showed earlier. So the first thing you're going to do, get out of here, is, so if you go to the instructions in the chat, you can click on these links with me. You're going to click on go to this URL is Earth Data NASA, and you're going to register an account. So here, let me do this in like a private tab thing. I'll copy this link and then new private window. Put the link in there. So it should take you to this website. And then what you want to do is click register for a profile. And then, yeah, just do a username, password. It'll ask a few things. You can lie, it's fine. And then you might have an email confirmation. And then once you verify your profile, we can start downloading data. So I'm going to give like the next 5 to 10 minutes for this to happen. And if you guys could send a reaction or maybe like a 1 in the chat or something, just so I know that like tons of people have successfully done this. Just put like a 1 in the chat box once you complete it. And if you need any assistance, just let me know. Yeah, so the first thing you do is go to this link. and it's in the chat instructions #1. That's true. Thank you, Randy McCarty. Just anyone interested in like their own privacy and security. I don't want you to feel pressured. Thank you, Lucas. Sounds like you have an account ready to go. Thank you, Claudia. Just gonna set a little timer for myself. If we get like 20 or 30 ones in the chat, then I'll move on. Thank you, guys. Awesome. Looks like tons of people are getting it. I think we have 14 or 15 people ready. It's only been a minute. Give a couple more minutes. Just in case anyone missed it, we are signing up for the Earth data service so we can download some VIIRS data into a coding exercise. So it's this link. If you go up in the chat, I have copy pasted the instructions. Just the first link, register for an account. If you've registered your account and you're ready, you can go to the next link in the instruction set. But I'll copy paste these links again. And just make sure you're logged in. And when more people are ready, I will show you how to download the data. It's not too difficult. I think it'll be like half a gigabyte of data, something like that. Not too much. Okay, I think we have like 25 people ready. Is anyone who wants to participate not have an account registered yet? Maybe put a 0 or something. Okay, looks like people are getting it. All right, and this will take a little bit, so you can catch up while I keep going. About 4 minutes there. So we're going to go to this. I'll copy paste it again. Going to go to this next link. We're going to go to this link. This is, I'll click on it here. This is the NASA LAD stack. So all over the US, there's these things called DACs for NASA and other organizations, and they're like distributed data access centers, something. I forget what DAC stands for, but they have like the data there, like stored on tape and hard drives, and I think they might be going to the cloud at some point. Anyhow, there's a ton of NASA NOAA data hosted on here, and this is where I get most of my research data, at least for VIIRS and MODIS type instruments. I'm just going to go ahead and copy paste the whole instruction set again, just so nobody's lost. So the first thing we're going to do is go to this sensors tab in the top left. It should be marked all sensors. And then we're going to scroll down to VIIRS JPSS-1. So that's the satellite mission of VIIRS, of the NOAA 20 VIIRS. And we need the imagery, and we need some geolocation, sun view geometry information, just a bunch of angles and metadata. So we want VJ102 mod. So that's VIIRS JPSS-1, and the product is 02 moderate resolution. And so select that, should turn green. And then VJ103 mod. And then don't ask me why, but to get the cloud mask, go back to the top left. It should say VIIRS JPSS-1 now. And select VIIRS NOAA 20 at the bottom. And now you can select Cloud Mask Level 2 VIIRS NOAA 20. If you've done this successfully, up in the top left under the Products tab, it should say 3 products selected. And if you click on it, it should say VJ102, VJ103, and Cloud Mask. If you've gotten this far, put a 1 in the chat. Let's see how everyone's doing. All right, cool. So just a quick refresh to see this product. Top left sensors, JPSS-1. How do you get sensors? Yeah, so in the top left, it says all sensors at the beginning if you load the page up from the link. All sensors, scroll to the bottom. There's a bunch of satellites in here, a bunch of instruments. Go to JPSS-1. Yeah, VJ102 mod, VJ103 mod. And then for the cloud mask, go to sensors again. To VIIRS NOAA 20. And select cloud mask level 2 VIIRS NOAA 20. So I have 3 products selected here. You should see the same thing. And now we're going to go to the time tab. So at the top, there's this blue oval, and we're in products. Now we're going to move to time. It's set on date range right now. We're going to go to single date and select August 7th, 2024. You can do any date, but this is a clear day with a good view of the park fire. So we're going to do this one. Yeah, so when I do a research study, I'll put a date range of like months, and I'll make an order, and I'll download the data. And I'll do it multiple times, get multiple years, multiple fire seasons. So then once you select August 7th, 2024, add the date. And then on the right, it should pop up that date selection 2024, August 7th. Any questions so far? Feel free to put it in the chat. The next thing is the coverage selection. So we don't care about the day-night boundary or the night, so just uncheck that. If it's checked, just the day. So we're looking at solar reflective bands. So these only work during the day when the sun is shining light on the earth. So just daytime. VIIRS does collect data at night. Thermal bands and day-night bands, if you're interested in those. Okay, once you have August 7th, 2024 selected and the day for coverage selection, we're going to go to location. That's the next tab at the top in the blue oval. And just drag the map and zoom in on California. That's the western US over here. If you're not familiar with US geography, here we are, North America. This is the West Coast here. And this is California right here. And on the right side, there's this menu. And I'm going to hit Draw Custom Box. And I'm going to draw a box right here. So what this does is we've selected the products. We've selected a date. And now we've selected this location. So now any files that intersect this box at this time will be loaded in the next tab. So just choose a little area in Northern California. This is about where the Park Fire and the Dixie Fire are. And then if you click on Files in the next tab at the top, it'll load all the files that are there. So I've gone ahead and looked it up, and the ones we want are at 2054 UTC. So there's a Cloud Mask file, a VJ102 mod file, 2054, and a VJ103. To download this is super easy. Just click this down arrow on the far right of the table and download those three files. So VJ103, 2054 UTC, VJ102, same time, Cloud Mask, same time. I'll stay on this page for a couple of minutes. If anyone has any trouble getting to this point, just let me know. If you're able to download these files, it requires an organization for me to download. Must have done something wrong. Okay, error, loading image. Yeah, you don't need to load the image. If you download the file, you will not be able to open it unless you have like Panoply or some special application. But we're going to do it in Python. If you try to load an image in this website, you don't need to do it. We just need to download these files here. So if you click Image Viewer, I don't know, it might fail. If you go to Images, yeah. We just want the search by product. Yeah, if it says it requires an organization for you to download, make sure you're logged in. So at the top right, there's a login, and I'm logged in right now, so it's giving me the option to log out. Yeah, just download, Paul. Yeah, just download the NC files, the .cdfs. So if you just hit the down arrow, it'll download it. Organization required. I'm not sure, Crystal. Is anyone else having this error? You want to download, it says organization required. Maybe if you go to your account on the Earth data link and put an organization, it might work. Thank you, Hamali Patel. They say, I think if you put that you work government sector, it requires you to put which organization. It worked for me that way. Okay, I think everybody who can, I think everyone understands basically how to download the data. We can talk more, but I'm going to move on to get the Python notebook set up. So if you're still downloading data, just shift your focus to me again, and we're going to look at how to bring up the code. And then you can go back and look at the data, see if there's any more problems. Okay, so I'm going to drop a link to the GitHub, just has a notebook in there. If we go to this, if you go to the GitHub, I made a repository and I put this notebook in there. And I put all the code that you need, everything. The only other thing you need is the files that you downloaded. And now we're going to go to Google Colab. So I wonder if I can just if we just Google Colab. I'll drop this link. So if you go to the Google Colab link, and then I think you'll need a Gmail account. So making this work was a logistical nightmare, but if you have a Gmail account, you can still participate. If not, if you have Python on your computer and you have the netcdf4 library, or you know how to install that, and matplotlib, please do. Please follow along. You can still use a notebook. If you don't have Python on your computer and you don't have a Gmail account, I think unfortunately this might not work for you right now, but feel free to look at the code and have it as a reference if in the future you want to do the exercise as well. Or you want to start doing satellite analysis or whatever. Okay, so click on that Google Colab link, you're going to hit File, going to hit Upload Notebook, and then there's these tabs on the side. So there's different upload options. Go to GitHub. There's a GitHub tab, and then take the GitHub link that I gave you and put it in there, and it'll automatically import the Python notebook. And then we'll go through the code together. So it's File, Upload Notebook, GitHub, and then put the GitHub link that I have in the chat. And it should automatically import the notebook. If you successfully done this, if you could put a 1 in the chat, so I can just see if people are following along. Everyone's getting it. Thank you, Molly, Lucas, Brandy, Clay, Megan. Okay, awesome. And if you haven't gotten it in the GitHub, I believe it shows the images that I produced too. And it's got some assignments at the end, a couple comments. So if you can't get this to work, hopefully you can still follow along and use the source code in the future. Okay. Okay, looks like we have 11 people ready. I'm gonna keep moving. I'll go slow. Okay, so you should have all this code. The first section is installing some libraries to Colab. The next thing is importing. We're going to use 3 libraries. And then I have 3 functions. One reads the cloud mask, one reads the geolocation and all the angles and stuff, and the last one reads in the reflectance bands. So I guess the first thing we can do is just hit Shift Enter on the first cell. Google Colab is going to tell you this code's not from Google. It's from me though, so run anyway. I'm a trustworthy guy. It's going to install it. It's just going to take a few seconds. Might take a little longer for you. I've already installed this on this notebook. And you'll know the install worked if you go to the next cell and hit Shift Enter. There should be a little check mark with no errors. And then NumPy should already be on the notebook, I believe. If not, you can do this command, !pip install, and then NumPy. Okay, let's see the chat. Hit what? Shift Enter here. Shift plus Enter to execute the cell. So these are called cells, these little blocks of code. If you click into the block and hit Shift Enter, it will run the code in line. And if you've ever used Jupyter Notebook, it's the same thing. Okay. A little detour. Oh. Also, you can hit the play button on the left when you're in a cell block. Thank you, Megan. Yes, we will go over the files soon. Brandy, were you able to download them? or are you just talking about getting them into Colab? I'll wait on that. Haven't gotten them downloaded yet. Okay. Let's take a look at was it that organization issue or some other issue? Okay, I'll work with selecting and downloading not complete yet. Okay, I'll come back to that. You keep working on that. I'm gonna start to go over the code, and then if anyone needs to catch up, you can join back in. And if you have any troubles, just put it in the chat, and I'll come back to y'all. Okay. So the VJ103 file, it's got latitude and longitude. I just selected it. I've made these functions myself. So it just takes the file name, and then I've set all these to true because I want all of them, just in case you do at some point. So latitude, longitude, solar zenith angle, viewing zenith angle, solar azimuth angle, and viewing azimuth angle. So these are just the angles that show the relative position of like the sun and the satellite to the Earth at a certain point. And include LWM, land water mask. So that's important. So it just opens up the netcdf file. It grabs a geolocation data group and grabs these variables. So I grab the latitude, longitude, solar zenith, sensor zenith, which is like the satellite, and so on. And I grab the land water mask, and it puts it into like a Python dictionary. And you wouldn't have to worry about that. I coded everything, almost everything up. The next function is the VJ102 file. So it takes the name of the file, the path, and then it asks you which bands. It's like a list, like band 1, 2, 3, 4, and so on. And it opens it up. It sets up an empty list, and then it goes through the bands that you want in a for loop, and it opens up the netcdf file group observation object, and adds them to this list, and then it returns the list of the reflectance bands. The cloud mask is hilarious because it's stored in a byte. So you have to unpack the byte. So I coded this in grad school, and I've been copy pasting this since 2018. So feel free to do the same. It just takes the integer, turns it into a byte, and then it reads the ones and zeros in the bytes. And then there's like a user guide to decode the bytes, like what they mean. So I've like decoded the bytes and I've already done everything. And the last function is to flip the array. Everything's like upside down and like inverted when you plot it. So I just have this flip function. So it's like north is north, south is south, east is east, west is west. So if you go to the top, you've installed everything, you've imported the libraries, shift enter, the play button. Define functions to read this. So hit shift enter on all those functions. So they're defined. And the next thing is reading in the files. So these files are on your computer right now, but we need to upload them to the Colab notebook. So I'm going to show you how to do that, and then I'll circle back with the people who haven't downloaded that. And once you have the files in there, then you can shift enter on everything and you can continue on your own, and I'll catch up with y'all again to show you what's what's going on and what I'm looking for. So on the left-hand side of the notebook, there's a folder. If you click on it, it brings out this window with files. And then there's an upload picture. It's this paper with the up arrow. And then you can upload the images. So I have VJ102 mod, right? And then I can click open. And then it's uploading here on the bottom. You can see it, and then it'll populate. So I'm going to do this for all the files. So VJ103. And the cloud mask. Is anyone still not downloaded the files yet onto their computer from the NASA Lad stack? Okay. Okay, Brandy, what I think I'm going to do is I'm going to put the files in a Google Drive, and I'm going to give you the link, and then just request access, and it'll give it to you. I think that should work. I just didn't want to do it for like 70 people. I'm going to stop sharing and do that, and I'll come back. So if you weren't able to download those files via the DAC, it's okay. I put the files in here. Just open it and then request access, and I will grant you access. And when you ask for access, just send something in the chat so I'll check my email. Okay, I see the share request coming in. Oh, there's so many. All right, I'm gonna get to all of you. Don't worry. All right, there's like 20 of y'all, so I'm getting it done. Yes, no problem, y'all, no problem. I'm glad y'all be able to follow along. Did that give you access to all the files or just the VJ103? Just curious. One oh two, 103, just that. Oh, this should put another link in. This should be the whole folder. Oh, I'm sorry. Looked like it shared just the file. Okay, I'll do everyone again for the whole folder. Hopefully that'll work. This feels illegal, just like not even looking at your names, just like share, outside organization, you can have it. Okay, I'm getting more emails in to share the whole folder. Please hit that second link and request access so I can give you access to the whole folder. Sorry about that. And go ahead and upload those files to Google Colab. Okay, cool. Yeah, download those files and then put them in Google Colab. You might be able to link them directly from your Google Drive. I'm not sure. Whatever works. I'm gonna go back to the code now. Okay, so once you have those files uploaded, as I'm showing in the left here, the whole code should work. If you get an error, just check the file name. It should be this. So I'll go ahead and do it myself. Oh, it looks like it's running. VJ103, that file wasn't found. Let me see what the name is. You can just hit the three arrows or three dots here to copy path and put it here. I just take off this content thing. Oh yeah, mine had this one thing. I think I took that off for yours. This should work now. Cool. Then the cloud mask file, run that. Thanks, Amali. All right, and then If you hit the first plot, which might already be plotted, I'm just using matplotlib plt, so I imported that at the top. Over here, we installed that, and we're just doing a plt.imshow. Imshow is a function that can plot an image. So image show, and I've taken the bands. So in the box where we open up the VJ102 bands, I took band 11, 7, and 5. So that's 2.25 micron, 0.86, and 0.67. And it's put them in a list in this order. So when you plot it, it's already the Dayland Cloudfire RGB. I flipped the array so it's like oriented in the right fashion, and I have that functions here. I just flipped it over the row axis and then flipped it over the column axis, so it's oriented correctly. And then I've zoomed in on this part of the image. So if you want to see the whole thing, you can put what do you call that? Parentheses, and then a pound sign or hashtag. Hit it again. It'll show you the whole image. So if you plot this in like your own Python, you can like zoom in and like you'll see the white spots. But I just manually zoomed in by selecting this part of the array. So here's the park fire. Are people getting that far? One in the chat if you got this far. Because if you got this far, everything should work. Maybe some people are uploading and stuff. Awesome, I'm seeing some ones. Still need permission. Thank you, Brandy. I will grab that. Oh, I see some permissions. Yeah, sorry. Here, I'm gonna stop sharing my screen and give those permissions. Share, share. Okay, I just gave like 10 more people permission, I think. File not found. If you get a file not found error, did you upload them? Lucas, did you upload those to Google Colab yet? Yes, you did. Okay, so did you copy the path of the file on the three dots and then paste it into like where I define the file name in the code? Okay, so is there the slash content slash thing there? If there is, just delete that. Yeah, delete that part, the slash content slash. I don't know why Google says that's the path name and then it's not the path name. So just put the file name itself and it should work. So I'll share my screen again to show that. So it should look like this for VJ102. Yes, it needs the quotes. You can use double quotes or single quotes. Okay. Okay, Wei, if I'm pronouncing that correctly, W-E-I, Wei Zhang. If you successfully uploaded the files, they should be here. If you get an error, maybe you downloaded another file or something, hit the three dots next to the file of interest. So for you, VJ102, hit copy path. That'll copy the path to your clipboard, and then replace the file name with that. Just copy paste, and then delete the content slash the slash content slash, and then it should work. And the same for the rest of the files. Okay, I see a couple more share requests. Wait, did that fix that? And Lucas? No, maybe a corrupt file. Oh yeah, maybe try at the top. Thank you, Hamali. Try at the top importing netcdf4 again. Maybe it looks like it's a netcdf, might be a netcdf error. If the import doesn't work, try that box where I pip install it and then import it. File not found error. Okay. Is anybody else having any issues? Okay. Okay, Wayne, Lucas, I'll come back to you. Keep try to like pip install the netcdf4 at the top again, import it again. Yeah, okay, Claudia. Don't know where to find the path of the files. Here, I'll show again. Share screen. Okay, Brandy, the path of the files. So if you've uploaded them here and you click the three dots, you can get copy path, and then you can paste it anywhere you want. So I can, is there paste? I'll just do Command V or Control V for paste. Then delete this slash content slash. Yeah, and then this should work. So there's some people just downloaded the files and uploaded them to Google Colab. Leonid, what are the access units of the images? They are the pixels. So if I just show the whole image. So this image is made of pixels that in the center are 750 meter resolution. And as you go farther out from the center, they degrade to like 2 kilometers or something. They degrade in resolution. So the pixels change in size. The axes are which pixels. So they're like 3200 by 3200 pixels. So you're seeing about 3200 by 3200 kilometers, give or take. And then if I zoom in on like I've zoomed in on this section here, now you're seeing like 500 pixels by 900 pixels, which is what I have. I did like 500 pixels here, like 500 to 1000, the rows. And then I selected 1000 columns of pixels, and then I selected all three bands. Okay, I'm just going to move on real quick. So the next step is the cloud clearing step. This is a very basic form of cloud clearing where I'm just going to take out the cloudy data, and that's it. So the next box, I make a copy of the bands because we're going to modify them. And Jupyter Notebook, the way it handles like arrays stored in memory, you have to do this. So I make a copy, np.copy. And then I take the copy, and here's the cloud mask. And where the cloud mask is 0 or 1, I set it to numpy.nan, not a number. So you see there's a bunch of clouds and smoke here. I get the cloud mask. Anything that's like a probably cloudy or confident cloudy, I set to nan. And I plot the image again. And the image has like, I took out all the cloud data. Thank you, Megan. So if you've gotten this far and you've cloud cleared the data, I have a few exercises that you can do. And just if you have any questions, just throw it in the chat. I can help. So the first one is calculate the true color image and plot it. So I have some hints. So you'll need to get new bands using the VJ102 function. And you can Google the Veer's band specs to find like which bands you need. So you're going to need red, green, and blue. So to make the true color image. The DLCF RGB. So that's just this. So you already made it. So, but you can practice using the function. And the next thing is the normalized burn ratio. I guess I haven't shared the slides with you, but if you Google the normalized burn ratio, you can find like which bands it is. It's the 2.25, 0.86. Look at a Veer's band spec sheet to find the index, like the band number. Call the VJ102 function. You can do that. If you have time, you can try and threshold the image to just show the burned areas. And this is a cool analysis because I'm catering this towards burned areas, but you could do any kind of image classification, any kind of masking that you want. So if you have no issues, please continue with the exercise. If you have any questions, feel free to ask them. I'm going to give some time for the exercise. If you are struggling with parts before this, also tell me in the chat. We'll figure it out. Right. How can I show on screen the lat long edges of the box? So you actually can do this. So VJ103, if you go to that, this returns a Python dictionary. So if you go to the definition of the VJ103 code, there's a Python dictionary with all these keys. One of the keys is latitude, and one of the keys is longitude. And the latitude array is an array of the same exact size of the image, but with the latitudes, and likewise for the longitudes. Okay, Lucas. Were you able to upload the 3 files to Google Colab? Yes, I was able to download to Google Colab. Okay, cool. Were you able to pip install here? I'm showing it to at the top, the netcdf4. I'll get back to you, Brandy. Don't worry. Okay, and you were able to import netcdf4 from netcdf4 import dataset. Okay, cool. And did you run the cell with all the functions in it? Just the cell, shift enter. Okay, file not found. Let me try and replicate it. So if I put, I feel like you probably have the right path and something else is happening. But let's see if I just put some. Are you sure you have the right file name? Because I get that error with the wrong file name. Can you in the chat put the file name that you're using in the code, and then show the file name that's in the Google Colab folder? Like send both of them. They should match. Brandy, what I would suggest if you're trying to do Google Drive and then get the files into Colab straight from the drive, what I did is I downloaded them to my computer and then I uploaded them manually to the Google Colab, and that worked well for me. Okay, cool, Brandy. Megan, I will give you access. Okay, you should have access now. Okay, Lucas, it sounds like you're doing everything right. So if it looks like my screen, it's still not working, I'm not sure. I'm not sure what to do. Okay, for NBR, you need bands 11 and 7. So it'll be like I'll put it in the chat. It'll be like the reflectance at band 11 minus the reflectance at band 7, and then divide that by a sum. But then before you calculate that, you need to divide. Some people don't do this, but I think you have to. So for each band, divide by the cosine of the solar zenith angle. The solar zenith angle is you can access it like this. It's in that VJ103 dictionary that we made. So divide each band by the solar zenith angle and then do this formula. So the reason I like to normalize by solar zenith angle is to correct for the sun angle, because the sun angle is going to change depending on your latitude and the time of day. So if you're looking at like a lot of data throughout the year, in different parts of the world especially, but also throughout the year, if you want to de-diurnalize your data and de-seasonalize it, I like to divide by cosine of solar zenith angle. Through Google Earth Engine, yeah. A lot of people are using that these days. What do they know about normalized burn ratio, huh? What does Google know about that? I think we'll go for like 10 or 15 more minutes, and then we'll make this idea. So the satellite images y'all produce, we're going to do a mesoscale precipitation discussion, just like I showed in the slides. I'll show it again. We'll start right now. So as when you've completed like the exercises or you've had enough, you can make a figure like this with a satellite image, maybe in like a Google slide or something, and just pretend there's a rain event and draw like a little flash flood warning and put like a little message like burn scars, enhanced risk for flash flood warning. I want to make like a little collage of everyone, and then you can send it to my email. Put my email in the chat. Maybe we can have like a cool little image come out of the exercise with everyone's little weather prediction. All right, I'm just setting a timer for myself for like 10-ish minutes. Is this code and slide shareable? Yes. It's on GitHub and it's public, so feel free. Could you share the link? Yes, I will reshare the GitHub link. Okay, as you advance through the exercise, I'll leave the IDSS activity here, the Information Decision Support Services. So imagine your product is going to go out to stakeholders. They want to know about flash flooding. You put in the satellite image that you produced of the park fire. And I have some instructions here. Just create a graphic with a fake rain event. You can put like a blob, like a circle, and it means it's going to rain here. And write like a little message beneath it of the warning, if you want to, and send it to me with the subject burn scar flood graphic. And I'm going to make it into a collage. Maybe we can send it back out, or a little way to remember the time. We had a good time. Could you please repeat the last part again? Yeah, sure. So once you get like some images of the park fire, I'm sharing my screen right now if you don't have it up. I have a slide called IDSS activity. So I want y'all to make your own version of this product. The mesoscale precipitation discussion. So there's that park fire, there's a big red blob in the satellite image. Just put like a fake rain event over it, maybe like a polygon or a circle or a square or whatever. Say like it's going to rain here, flash flooding possible due to burn scars, like enhanced risk of flash flood. And with a little message, you can label the plot whatever you want, and then send it to me. Send me like a screenshot or a Google slide at my email here with the subject burn scar flood graphic. And I'm going to make it into a collage. It's see if it's cool. I don't know. Put everyone's work together. Okay, cool, Hamali. Yeah, if you want, you can email me the picture. And just real quick, send me the screenshot and I can tell you. Okay, this is how you calculate the normalized burn ratio. I'm showing it right now. And so the reflectance at 2.25 microns is band 11. And the reflectance at 0.86 microns is band 7. So we grab those using the VJ102 function. And then you divide that by the sum of those bands. And there's nuance if you have time. In the VJ103 dictionary, if you go to the definition of that, we in the variable, you can select the key solar zenith angle. You can use numpy.cosine, calculate the cosine of that entire array. And then for each band, divide the band by the cosine of the solar zenith angle. And it'll be like array divided by array. So it'll figure it out. Like Python can handle that because the arrays are the same size. They correspond. Each pixel corresponds to its counterpart in both arrays. So take each band, take these two bands, grab them, put them in a variable, divide them by cosine Euler zenith angle from the VJ103 dictionary, and then stick those modified reflectances into this formula right here. And you should get a map that looks like this on the left. So this is the park fire. So it should be like the vegetation should all be really dark, depending on the color map you use, I suppose. I use the jet color map. You may mess around with the Vmax and the Vmin of the plot values. I'm in the Q&A section. Diana says, I wonder if it is possible to use data from Amazon to create the same with VIIRS only. Yeah, if you find the VIIRS data on the Amazon cloud, you could definitely do that. Or with Amazon resources, like if you have access to cloud computing, you can definitely put the notebook up there. Yeah, EDR data, yeah. My functions may not work with those files, so I'm using the 6-minute granules. But I'm sure there's other people who have wrote functions to open those files and get a similar result. So for normalized burn ratio, you should have very positive values for the park fire burn scar, like close to 1. And then the vegetation should be negative, and desert near 0, something like that. I'll show Hamali's. So you can see the park fire is bright, has higher positive values. The desert is like a little bit dimmer. All this vegetated land here is dark. It's negative. Here's water and clouds. Bonus points if you cloud clear this. There's the land water mask is in there too. You could take out the water. Okay, just one final reminder in the exercise. If you have time, go ahead and create like a little fake flash flood product, little flash flood warning using your satellite imagery. Use whatever you think looks best, that dayland cloud fire, maybe the normalized burn ratio if you got to that. You could use some true color imagery too. Whatever you want, put it in a Google slide, take a screenshot, and email it to me. And I'm going to turn it into a collage. So go back to the 5 questions. So why is tracking burned areas in near real time from satellite important? So satellites get instantaneous coverage of large areas for all regions across the world. So you don't need to have sensors or people or flying planes around. They're already in orbit. Most of the data is free. It's very convenient. The disadvantages and advantages of active and passive remote sensing versus polar and geostationary, and also polar versus geostationary satellites for change detection. Active can see through smoke and clouds, like with the synthetic aperture radar. But it's not always on because it has a lot of power draw. Passive can always be on and scanning, which is really nice. Polar always has better spatial resolution, polar orbits, and geo orbits have much better time resolution on the order of minutes, where polar, you may be waiting a week for a revisit. So how do burned areas recover, and what is the impact change over time? So typically 1 to 3 years with vegetation regrowth, although not all growth is equal to what was previously there. So there may be different flash flood properties to the land afterwards. Where can you download and view the satellite data? So the Copernicus browser, which I showed, and the NASA Earth Data browser, which we all made accounts on. You can do the same for Copernicus. For viewing, we looked at NASA Worldview, the Copernicus browser, Cirrus Slider. There was also a link sent on Himawari 8, and there's UMET View as well. You can look at the Meteosat satellites and some of their polar orbiters in Europe. And then one of the last things we did, how do you open and manipulate the satellite data in Python to see burned areas? So I just put the libraries that I used, and feel free to share and redistribute that code. That GitHub link is public. After the session, the slides will be available, so you can have all of the links and all of the formulas and reference data. Yeah, that's it from me. If anyone has any questions or